Now we are going to discuss a new kind of graph which is called directed graph. Again, the same definition looks the same. However, now we have changed the definition of edges again. Now edges are not unordered pairs, but they are ordered pairs, and they are written as E is a subset of V cross V. Accordingly, we change the definition of path. Again, the path is V1 to Vn such that Vi comma Vi plus 1, an ordered pair, is element of E. The main change is this notation of writing down the edges. For example, here is a graph which is a directed graph now, where every edge is given a direction, not only the connection. So again, it's written as a V comma E pair. A, B, C, D are the element of V, and edges are now written as a pairs rather than sets of two elements. Now there is additional complication that there can be a path between two nodes in one direction, but there may not be any path in another direction. For example, there is a path from A to D, that goes via B, but there is no path from D to A. Now we can define strongly connected components, which is different from the connected components, as follows. G is a strongly connected if for each pair V comma V prime there is a path from V to V prime in E. A graph G prime is a strongly connected component if G prime is a maximal strongly connected subgraph of G. Let's look at an example. Here is a directed graph. You can see there are three different islands, A, B, D, C, and E, F. And these islands are strongly connected components. From any node in a red color node, you can reach to another node. For example, you can go from A to B, B to D, D to A, and D to B. In all combinations are possible. But you cannot go from A to C. From there, you cannot come back from C to A. So therefore, they cannot be part of same strongly connected component. Now let us define SCC graph of a given graph G. So SCC of G is defined as follows. Let's suppose C1 to Cn be the SCCs of G. For every SCC Ci, we define a vertex Vi in the SCC of G. And now the question is, how do we connect these nodes in SCC G? So if there is an edge between Vi to Vj, if there are two vertices Ui, Uj in G, such that Ui is element of Ci, Uj is element of Cj, and there is a connection between Ui and Uj in the original graph. Let's look at an example. Here is a directed graph, and this graph has three strongly connected components, C1, C2, and C3. Since there is a node in C1 that is connected to a node in C2, there is an edge. Similarly, there is an edge between C2 to C3, there is an edge between C1 to C3. However, you see that there is no edge that goes from C2 to C1 because there is no green node that is connected to a red node. Now, here's an important fact about SCC of a G. It says that if you have a directed graph G, its SCC G is an acyclic graph. Now let's see the proof. Let us suppose there is a cycle in your SCC of G, and that graph is denoted by V prime E prime. So there must be a node UU prime such that there are paths from U to U prime in the reverse direction. Let C and C prime be the SCC in G corresponding to U and U prime respectively. There must be a path from nodes in C to nodes in C prime and in the reverse direction. Therefore, C and C prime cannot be SCCs because now they are not maximal elements anymore. They are themselves part of a larger SCC. Therefore, there is a contradiction, and therefore there cannot be a cycle in your SCC of G. Now this suggests that a directed graph which does not have a cycle is of important significance. So therefore there is an explicit definition for such graphs, which are called DAG, directed acyclic graph. A directed graph G is DAG if G has no cycles. Here's an example. The above graph is an acyclic graph. You can also define a tree from a DAG. The answer is simple. If there is at most one path between any two nodes, then this is a tree, otherwise it's a DAG. Now let's extend the definition again. Now we introduce a label to the edges. Usually when people draw graphs, they just not only say that these two edges are connected, they usually name the edges also, as assign some number, some string to the edges, which we call labels. So in this setting, we will say edges is a triple consisting a node, a label, and node again. This is written as V cross L cross V. Here's an example. You have 4 nodes and they're connected by 5 edges, and now you can label each edge, and you can notice that there are 2 edges connecting A and C. They are differently labeled, therefore both can exist without calling E a multiset. Notationally, you can see that when you say L, you need to define the type of your labels. For example, here it's integers, and when you write edges, you need, instead of writing pairs, you are writing triples where the middle element is a label. So we have seen various versions of the graph definitions, and now we are going to look at how to represent these graphs on a computer.